So let's do a review just on the most important concept I guess we introduced last time is the entropy. So think of any random variable x here. So like let's say a random variable x here, and there's a source x here. So it's described by the some distribution px, let's say. So basically, the entropy here is roughly speaking, is a, I guess it's a, not just roughly, more or less describe like how much information on average for each of the sample of the variables. So how you can interpret that, like most naturally will be you consider if I have a source here, if I'm trying to pull out like a sequence of source here from this sequence of like random variable or like a realization of this random variable from this source here, we want to know like on average how many bits are required to store this information, store this realizations here. And per sample on average, that will be like that entropy so many bits. And and similarly, if I have the conditional entropy like hx given y here, so it's basically it it describes like how much information of x or remaining information of x, given that we know y. And also this is average, also average over like samples. So so the way to interpret that, like again, I can have like a source here x here. Now I have a site information y here, let's say y, like or like some other information y. So I have some kind of encoder here, right? And this encoder, I'm given not just the input x, but also this helper information y here. And then if I want to perfectly recover this x back at the decoder, so at the decoder, I try to at the decoder here, I would be, I mean, the decoder will be also like given y as well as the helper information. So we supposed to recover x hat, let's say. So per sample, on average, how many bits are required to to store this x, basically, given this helper information y, will be precisely h is given y. And is that clear? And we have given the forward proof for this one, for hx. This is usually known as the source coding theorem. It's precisely stating exactly the same thing I just mentioned. So it's like given a random variable, um, on average, we only need hx so many bits to compress x. And in other words, like if we give less than hx bits, then we won't be able to recover x losslessly. And also, like if we give it more than hx bits, then apparently like we can recover the we can find a scheme to compress x so that x can be compressed and then recover losslessly. So the forward proof, as I mentioned, we use the concept we introduced last time is the is typical sequence. For typical sequence, we say that like any sequences will be typical. So of course, the sequence will be a samples of these random variables. Let's say x1, x2 up to xn here. So maybe I just shorthand to x bar here. So like I don't know whether x bar is a good thing here. Maybe I put a bar underneath that. Um, just not to be confused, this is an expectation of x. So so let's say this vector x here is a sequence of x1 up to xn here. So if it's typical, if we do remember that typical, then it's more or less okay. The precise condition is like yeah, it's okay. I just give a what thing. So it will be typical if the probability is approximately 2 to the minus n h x, something like that. Okay, this n and this n should be the same. Maybe I use smaller n here. And and this is shown by law of large number that we proved last time. And okay, basically what's happening is that if we sample any sequence from this source, like basically just sample this source like n times to get a sequence, something like that. By law of large number, that sequence will be always typical. And basically, all all the typical sequence will yeah, so all the sequence will be typical. Okay, I guess that's okay. And then since all the sequence that is typical have the same probability, then we can argue that like the number of typical sequences here will be just 1 over this probability will be just 2 to n hx typical sequences. And so then the forward proof is very simple. Basically, just do counting. So we have like some source here, x here, and we are drawing sequences here, will be this x bar here. And then we will just basically label all the typical sequences, although we have exponentially so many of them. But okay, assume we can do that. So we just label that into x1 up to x 2 to nhx, let's say. All of them I will label like 1, 2, and so on and so forth. And then we'll just like whenever like we pull out a source from this or like pull out this sequence from this source here, we'll just compare which one it is. And then we'll just send out the labels, right? So okay, this will be like maybe K here. And since we have like 2 to NHX, so many of them, so we just need like NHX bits to store that. So therefore per samples, we just need HX bits, right? On average. So this, although this scheme is kind of what I want to say is imaginary, that you cannot actually implement that, but this shows that like that will be a scheme. At least there's one scheme is this scheme, although like it's not practical. There'll be a scheme like that. You will be able to compress any source that with entropy hx with like just hx bits per sample. I'm able to recover that losslessly. And actually, before we and then we talk about the Converse proof for that one. The Converse proof will be basically saying that like if we okay, yeah, let me put okay, the Converse proof is basically saying what? Converse proof is saying that like if we have we have if we compress the source more than the hx bits, so basically let's say the weight here, I call this weight here just r here. If r is less than hx bits, then definitely we won't be able to recover the original x perfectly. So therefore probability x not equal to x hat okay won't be 0, something like that. So and okay, before we go to this one, let's say. Yeah, sure. I will. I will. Actually, I actually talk about. I didn't talk about Yangtze inequality yet. Actually, I will go through this Converse like immediately afterward. But before I go to the Converse again, I guess I also like to just quickly describe the forward for this one also. Like when we have like the helper information, the idea of the forward, like in this case, almost the same. So the way you think of that is like, okay, since I have helper information, right? What we can do is like, let's say I have just imagine that like I have this px given y, something like this conditional uh, distribution here that will sample. I mean, we output this sequence of x here. Now notice this source is almost like some kind of source parameterized by by the helper variable y here. So if we have a different y, let's say if I have y1 and y2, essentially we have a different distribution. We have like one distribution, the px given y1 can be like that, and maybe like okay, this color may be too bad. Maybe this is a px given y2 can be another distribution. And now when we have if we think of like we have a sequence coming in of x, a sequence of x and y coming in together at the same time. So I have a y here coming in as well. So I have like x1, maybe I just say a particular realization. I say that this is x1, x2, x3, and so on. Maybe y, I just give a label here, y, 1, 1. And then this is a 2, x4 is 1, and let's say something like that. Now, what we can do is like, we can think of like, whenever we have a different y, we just use a different encoder and decoder pairs. So for example, if I have like the alphabet size of y is, let's say, is a just y the square y here. The alphabet size is a square y like this. This is the alphabet size of that. Maybe just 10. This is the alphabet size here. That means that like there's 10 different value of y's here. So then I can just prepare 10 different encoders and decoders, right? I can encoder 1 up to like encoder 10, and then I have decoder 1 and decoder 10 and so on, right? So according to which y I'm receiving, for example, if I receive first one is this one, y is equal to 1, secondly, like in the second time instant, y is also equal to 1 and so on. I'll just use encoder 1 and decoder 1, right? Because this helper information is available at both encoder and decoder. So I know like, okay, the decoder also know like which one I should use like at each time instance. Now in the third time step, I will switch to encoder 2, let's say, right? Now if I just look at like for encoder 1, the time I use encoder 1, then the distribution that I'm looking at, the x here, is essentially looking at the distribution p is given y, right? So then just for encoder 1, when I'm using, okay, this is a question here. When using encoder 1, that's for example, like at time instance step, at time, for example, at time 1, 2, and 4, on average, this is very important, how many bits are needed? Oh, okay. I hope you at least you can hear what I said. My handwriting is horrible. Needed to store x. Of course, it's given y, right? Y is given. Actually, oh, how many? Okay, how many bits here? Also, like per sample. Per sample. Per sample meaning per x. Oh, the question is here. The question is, when using encoder 1, or like at the, when I say when at the, that's it for this particular example here. Yes, I know. Yes. Let me try to write better. Like when using encoder 1. So in this case, in this particular example here, that's basically at time instant 1, 2, and 4 here. We receive a y is equal to 1, right? So therefore we use encoder 1, right? So for example, like that's at one time 1, 2, and 4. And at those time instance, on average, how many bits per sample are needed maybe I just if I have a better table, it'd be nice. Let me remove this keyboard here so I can just write on. Needed to store x given y. Actually, there's a hint here. Like I already used the information y here. You can ignore this given y here. You see, like we already used the information y. We switch to encoder 1 and decoder 1. That's essentially use that information y already. Okay, just think of like for the case like when we're using encoder 1 here, that's basically a times instance, this one, and this one here. Let's do a contrast here. So let's go back to this one here. If we don't use the side information, so if we consider the original source coding theorem, so we don't have the helper information, on average, we need hx bits per sample, right? Now, for the case when we have this helper information, we're switching from one encoder to another encoder. Actually, I should say switching the encoder decoder pair from one to another, like for each time instance. Oh, okay. Hx is the number of bits needed. Okay, hx is the amount of information. Oh, okay. And also one thing, like you should write capital X when you write hx. The reason for that is that the convention like big X is considered as the random variable and small x is a realization of that random variable. So, and when we say hx is on average, like how much information of that random variable, so therefore we want to write big X there. And so you can look at the expression there. The expression is exponential minus log px if you remember. I don't think you, yeah. But this is one thing it's good to remember. So the expression itself is like that. But it's important, more important, I will argue that like to kind of like um understand what is this expression or like what's the physical meaning of this guy means. It just means that like um on average oh, okay, in the most simplest form will be like how much information of that random variable x will be hx. Now to get a little a step more precise will be now how do I quantify the amount of information of that random variable? So one way to do that like very precisely will be uh, how many bits are required to compress the source per sample per each of the x such that I can recover the x losslessly, right? So if of course I can compress as much as I want. If I cannot recover that, that would be silly, right? So then let's say like how much I can compress. Essentially, that would be like how much information there will be, right? Apparently, I cannot compress more than the amount of information there, right? And I can also argue that like if the amount of information is like 10 bits, then I probably don't need to compress more than 10 bits, right? I mean, or like I don't, or I should say, I don't need more than 10 bits to store that way. Yeah. So let's see. I still need to use this keyboard. Let's see. Let's see. Since we have more than one encoder, it is 2 bits. Okay. Okay, let's maybe let me do like this, and then we come back to this. Okay, probably it's better. Like I I just give a couple numerical example, and we come back to this. Maybe that's better. So let's just give one numerical example. Let's say if I have x is a, say, remember the example I gave last time. So maybe it's just a, make it simple. Like it's a dice, but have like 8 faces. Let's say I don't know. Like I don't know how to call this. Like those dice have 8 faces, so have 8 outcomes. So if this is uniform, right? If x is uniform, then hx is, it will be just equal to 3 bits, right? Remember that. So because I now I have this each of this x coming out, so it can only be 1 up to 8 values, right? The value can be 1, 2, 3, 4 up to 8. So per sample, I just think of, okay, I just label that from 1 to 8. I don't need more than 3 bits, right? So definitely, if this is uniform, it'll be okay. Definitely, it won't be more than 3 bits. First of all, it won't be more than 3 bits. And also, like if it's exactly uniform, then this is actually exactly equal to 3 bits here. And this can be computed here. Let's say just for this example here, maybe in this case, like px is just equal to 1/8, right? So do a something like hx, just use this formula here, log px here, right? And px is just equal to 1/8, so we say let's use log base 2, so it'll be like log 2 1/8 minus, so it's just a constant, right? I can explore the expectation, that's just equal to 3 bits here. Now if I consider, let's say, uh, if there's more than 8 samples here, let's say if I have like 16 samples, I want 1 up to 16. So um, let's ask this simple question first. So okay, let's say that px again is a 116. Okay, so assume it's a totally uniform. So what is hx? So okay, ignore the previous question here. Let's say this is the first question. So okay, this should be simple enough, right? This is a 4 bits, right? And now if this is not uniform, let's say maybe I'll give you some numerical value, so you play with that a little bit, then maybe you have a more intuition. So let's say again, I go back to have like the the um, the alphabet can be 1 to 8, let's say, but let's say yes, it's yes. So let's say like I have px will be like, let's say I write something like p1. Maybe I just give some numerical stuff for you guys to play around at this moment first. P1 P2 is equal to 1/4. Let's say P3 P4 P5 P6 is equal to 1. Let's see, uh, 1/8. Wait, 1/8 is 116, I say, and then P7 P8, maybe it's 1/4 again, or maybe 1/8. I don't know. Yeah, it seems okay. Then yeah, this will add up to 1/4 again, right? So what is hx in this case? Question. No, note that it depends on the distribution here. So one extreme case you can think of is like if I have P1, remember I have the example last time, like P1, P2 is equal to 1/2. But let's say for the remaining P3 up to PA is equal to 0, then how many bits do I need? I will just need 1 bit, right? Oh, okay, yeah, but yeah, this is the second question here, that the alphabet is like from 1 to 8, but have a distribution like this. So it depends on the distribution really, because I look at this extreme case here. If I have also the alphabet size is like 1, 2, 3, 4, 5, 6, 7, 8, or like or the values can outcome can be 1, 2, 3, 4, 5, 6, 7, 8, but only the first two is possible, is one half. Then apparently I should only need not more than one bit to store that, right? Because the other outcomes never happen, right? Oh, okay, okay. Uh, which question you guys are answering? This one. So okay, it depends on the distribution. You need to compute that. Like it won't be 3 bits. The bound will be 3 bits because there will be 8 outcomes. I know that won't be more than 3 bits. Consider an even more extreme case. Let's say P1 is equal to 1. The rest are all 0. Then there will be no information, right? Because this is actually deterministic. It's always spit out 1 here. I don't need to store anything, and I can recover this at the decoder um, perfectly, right? Because I know it's always sending out 1. So at the decoder, it just need to spit out 1, right? It doesn't need to like do anything. It doesn't. Therefore, it doesn't need to store anything, right? Oh, okay. Okay, okay. Let me digress. Let me digress again. I'm sorry. Uh, you know Huffman coding? No, actually, I suggest that like maximum will be 3 bits, but you actually don't need more than 3 bits. You actually need less than that. HX will be less than 3 bits. Um, so I will come back to that question. Okay, let's again, like, since no one answered this question correctly, yes, it's okay. So since if I track correctly, I don't think like anyone answered this question correctly. So let's forget about this question first. So let's digress one more time to Huffman coding. Let me just yes, you can use the formula. Or maybe let's don't do digression for the moment since I feel that you guys are still interested to try to find to okay, let's just use this formula and compute this. So, okay, hx is equal to that. I'm given hx of the weighted, then you would take the hx of the weighted average. Um, yeah, it's like a weighted average. So, uh, okay, yeah, I don't know. Actually, maybe maybe Michael is right, but you can compute that. Like you use this formula. Do you guys want to try that? Like just quickly try that. See like what you got. Previously we have a kind of hand waving argument. I guess I didn't actually maybe articulate very well, articulated very well for this argument. I want to argue why this is so, but as I said, like we will prove this like precisely, right? Because we gave the forward proof already show that like you don't need more than hx bits to store the information. So therefore, we can argue that the amount of information is not more than hx bits. And if we can show that, like, if we compress more than hx bits, there's a we compress a weight less than hx bits, uh, we will always have a loss. I mean, we can never recover the original x losslessly. Then we can argue that the amount of information is exactly hx bits, right? So, but if you look at this expression here, this is basically something like weighted sum of like log px, right? For this each of the outcome x here, right? And I can argue that this is the instantaneous information for that random for that outcome x. So it's like if something is like less likely to happen, then I would say it's more valuable if it happened. But if this never happened, then it doesn't count as at all as well. So then the amount of information for that particular instance is minus log px. But of course, I need to weight the sum by the actual number of times it actually happened, right? So therefore, I weight the sum by px here. So just make sure all of us are in the same page. Right? Can rest of you just try to see if you can compute this case? So again, let's continue. Like, okay, see like if you can. In this case, I just plug in these values to this thing very simply. So you get an idea like just I guess like some intuition like for the number here. So you get something less than 3 bits. So and we will show that why actually we will prove that later on that why is always like 3 bits is the upper bound, but we'll leave that later on. But for the moment, like I guess it may be yeah helpful like to your understanding. Maybe you just give a try so I can make sure that like you guys are following as well. So and if you at this moment if you are not convinced y is less than 3 bits, that's fine. In the next I mean in the next page I uh so so here hx is equal to expectation minus log px, right? Minus log px here. Sorry, this one I need to be careful. This should be like big X here. Now, what is expectation mean? If I have like, for example, if I have like fx here, I compute the expectation. Just means that like I have the fx for each of the outcome of x. I'm doing a weighted sum of fx, right? Weighted by its probability. Fx sum over x, right? So now the outcome here is like 1, 2, 3, 4, 5, 6, 7, 8, 7, right? So I'm kind of expect over minus of px, right? So for example, this would be a sum of like p. Yeah, you don't need to kind of like you don't okay, yeah. Hopefully you are not confused anymore. But this is a something like you just think of this as a function itself. This one thing I agree that like it could be confusing, but know that px is a function of x also, right? Because you have x is mapping into px is just basically if you have a x is equal to 1 here, you have px is equal to 1/4, right? When px is equal to here, like px is 1/4, so on and so forth. So px is a function itself. So log px again is another function of x also. So you just think of, okay, this is just a function of x, and then therefore it's a weighted sum of this function of x, right, weighted by the probability, right? Now, so therefore, like this would be like P1, for example, like this is P1 there's a minus sign. Let me pull the minus sign out. Minus log, okay, or pull the log P1 here, right? P1 log P1 plus P2 log P2. Okay, I pull out the minus sign already, by the way. And so on so forth, right? So you can just substitute in everything. So everyone is following now. So P1 is like 1/4, right? P2 is like okay, a quarter, also like P3, P4, P7, and P5, P6 is like 1/16. I believe you guys are right, 2.75. I don't know. So let's see. So maybe like P1, P2 is a log P1, P2 is equal to 2, right? Or minus 2, right? And then or I should say minus log P1 is equal to minus 2, right? Equal to 2, right? And then P1 is 1/4, so I have like 1/4 2. How do I say that? How do I write it? Times 2 or something like that. I have two, maybe two of them, right? And then I have four of this one. Four is like 1/16 times like this is like times 4, right? Plus like two of the 1/8 times say not 1/8 is 3, something like that. So this is 1 here, this is 1 here. So it's like, yeah, it's like, yeah, I think it's like 2.75, yes. So now, okay, if you guys just think of, okay, this is so we just plugging things into the formula, and you are not convinced that like the number of, on average, right, we can compress up to this number of bits here, then just want to check like, okay, maybe a poll question here. Let's see, wait a sec. So how many of you heard of like Huffman coding? This is just a poll, like just see like if you guys are still around. So it is a compression method. It's a classic compression method. There's a story about Huffman coding. It's like it's optimum in some sense if you have a discrete source. Yeah, discrete source. This is a kind of optimum. If also like you are compressing like per samples as well, and this is if I remember correctly, like Huffman was a student of Fano or something like that. Like he was in a class and Fano just give a homework assignment and as a whole open problem, and then Huffman like came up with the solution and become this very famous Huffman coding. So, but if I okay, let's see. I don't remember the numbers now. What do I have like 1, 2 is 1/4. Okay, 3, 4, 5, 6. Okay. So let's copy the question here again. 1, 2 is 1/4, right? I think 3, 4, 5, 6 is a 1/16, and then 7, 8 is a 1/8. Let's say. Oh, okay. And then the Huffman coding. Okay, again, like the objective of Huffman coding is devise a code such that like we can compress this source effectively or efficiently, right? And so now let's consider the input here. It can be like 1, 2, 3, 4, 5, 6, 7, 8, right? So okay. So the probability is what? Like this is a 1/2, sorry, 1/4, 1/4, 1/16, 1/16, 1/16, 1/16, 1/8, 1/8. So the intuition is that like, okay, if I compress this uniformly, or I should say like, if each of the code word is the same, for example, like I can use 3 bits, let's say, to store like these labels, right? For example, I can say 1 is equal to 111, or like 000, 2 is equal to 001, and so on and so forth. Then, of course, like this way, I will need 3 bits, right? To store like the values from 1 to 8. However, know that like this is not very careful way of doing things, because like some of the outcomes are more likely to happen, right? Or happen more frequently. And for those outcomes, I should assign a shorter code word, right? So I call this basically a code word. I'm kind of like, think of like I have an encoder here. The encoder is like given an x, I spit out a code word like for each of these different x here. So for example, if I have 1, I can say 00 is like something like that. And then at the decoder, I'm trying to recover back this 1 here. But as you can see, like this is not a good way of doing things if I map 1 into 000, because like 1 happens more often, right, than these others, right? So especially for 3, 4, 5, 6, I should use a longer code words, so that like, okay, and also one thing is like I cannot say, I cannot um shrink the code words arbitrarily, because if I shrink it arbitrarily, I will doom to have some conflict with these different input, right? So in the past, I would basically actually give a very in-depth like discussion of these things, but because most of you guys won't study like source coding, so I won't actually get into that. But I would just argue that like here, like up, I think it's all obvious that like you cannot shrink the codes arbitrarily. For example, like I cannot on average like put all the codes just like on average of 2 bits, right? If I have 8 outcomes here, because I would just, that's basically impossible, right? 00011 I will consume all the code words, and for the rest there will be a conflict of this. I mean, there will be overlapping. Like since I only 2 bits, then the rest of these um, outcomes must reuse this code words here, right? So this is just some kind of like some form of pigeonhole principle, like um, in whatever. So then, okay, what Huffman derives the scheme is like, okay, let's find a way such optimally assign the code so that like the less frequent um, outcomes will have a longer code word, and a more frequent sequence will have a shorter code word. So how it's going to do that? Like he has a procedure like this. So if I lay out all the probability here, I would just say find the ones that is shortest. Like let's say these two are shortest, then I'll merge them together. Like the combined the probability is 1/8, right? So I repeat this procedure. Now it's like I have a joint label here for these two outcomes here. So now I will only consider uh, this one, this one, this one, this one, this one, this one, this one instead. So I won't consider these two anymore, like separately. Now, if I look at the probability, like um, again, these two will be two smallest, right? So I merge them together, probability 1/8. Now I repeat the procedure. I may merge these two together again. I guess 1/4 here. So now the symbol that I'm considering will be like this one, this one, this one, this one. I'm a mega symbol of this guy here. Right. Now I repeat that. Like so, I should merge properties together. I merge these two here, so I get 1/4 here. Now next step, I can merge, let's say these two, let's say like get 1/2. Then I can merge these two to get 1/4. Oh, sorry, 1/2, and then I can merge these two to get 1. So okay. Now to generate the code word, it's just like stepping back. Let's say I consider all the upper branch to be 1, and then the lower branch to 0. Then I can assign code word like this. So basically, I can have like one will be mapped into just 1 1, and then I have 2 map into like 1 0, I think, like, yeah, and then I have 3 map into like 0 1 1 1, something like that. So let me see like if you guys are following. So how about 5? Like what should 5 be? The covert 5? This is a question here. Maybe I also do one more 4 here. Oh, okay. Okay, I guess you guys are following. Okay. Oh, wait. Not exactly, actually. Okay, 4 is like 0 1 0 1. Okay, you need to start from this direction. 0 1 1 0. So this is 4. So what was 5? 5 again. Yes. Yeah. Most of you guys are actually 0 1 0 1, right? This direction, right? 0 1 0 1. So okay. You see, okay, then you can compare. Okay, what's the average? Now look at like what's the for this one? What's the average? What is the average covert length? Oh, yeah. Oh, I can't should I say a covert length? Yeah, it's okay. Average average in the sense that average over the probability, the distribution of x here. So then you see it's equal to what? It's equal to 1 have 2 bits, right? If I look at each of them. So okay, maybe I write the number here as well. So in red here. So the simple one have 2 bits here, right? Outcome 1 has 2 bits. And 2 also 2 bits. And 3, 4, 5, 6 is 4 bits, right? 4 bits here. Right? And then like 7, 8 is 3 bits here. So you see this is precisely minus log px here. And if you compute the average covert length, this is exactly 2.75 as before. So in this case, actually Hoffman coding is exactly optimum. So the source coding theorem like kind of like show that like on average you cannot compress more than 2.75 bits, and Hoffman coding like achieve the optimum here is like exactly only need 2.75 bits. So you can see that like Huffman coding is not always optimum like this. Optimum in the sense of reaching the theoretical bound, because for example, if your probability is not exactly 2 to the power something, like then the number of bits will not be exactly can be round off. No, can be round off, will be exactly the desirable length of the covert won't be exactly an integer, right? So for example, if I have like px here is equal to 1 6, then log px will give you something like 2 point something, but it's not like you will need 3 bits to store that, way. So if you try to assign that using Huffman coding, you will ended up using 3 bits. That would be less efficient than the theoretical value. Like if you can assign like fractional number of bits, then you can be more you can achieve compress more basically. And in that case, like one way you can do it, of course, like this is a not very practical, but theoretical you can do it. It's like you can just group symbols together. For example, instead of considering one symbol at a time, you consider x here, right? So if you consider 2 symbols at a time, for example, like let's say this is a oh yeah, I'm quite sure you have an error here. So know that like your average is not average over 1 over a, it's average over the distribution of x here. So it's like this is like 2 times this is a covert length, right? This is 2 of them times 1/4, right? Plus like 4 of this guy here, 4 times like covert length is 4 times like 1/16, right? Plus like uh 2 times 3 times 1/8, yeah. So okay, uh I I guess here I'm a little bit okay. Let me repeat the last statement I just said. Like, so let's say if I have the probability of some outcome is not exactly a power of 2. Let's say it's like 1/6 something. Then if I use Huffman coding, I will end up like using 3 bits to store this, right? But theoretically, the optimum um, number of bits to store that will be fractional. It will be minus log px, right? So this will be something like between 2 and 3, something like that. So uh, one way you can get it a little bit better is to group some of the symbols together. For example, if let's say this x here, maybe I'll call it x1 here. This particular outcome x1 have a probability 1/6 here. So then maybe I can instead of considering x here, I consider x together and group them together as a super symbol. So therefore, like I will have probability of x1 that come out with a probability 1/36, right? And 1/36, let's see, will be actually this is not too good still. Like I will need like log 1/36. This will be maybe at least 6 bits here. It's not exactly a very good example. Let's see. Maybe I change it to 1/5 here will be better. If I change it to 1/5, again, like here, like using Huffman coding, I will need because log 1/5 will be like between 2 and this is between 2 and 3, right? And if I do Huffman coding, I'm forced to use 3 bits to store that, to store this guy here. But if I group the symbols together, I have like px1 have 25 is equal to 1/25, and log px1. So now this time will be bounded by, I think it's 5 and 4, right? Something like that. Yeah, between 5. Uh, yes, right? And then I only need 5 bits to store that, right? So on average, now I get a little bit more efficient. Yeah, you would like to do that, but the problem is like that. You can think of log base 3, for example, but it would be very difficult to design a computer to run like three different outcomes, right? Think of that. But why we are doing binary is just because of the circuit, right? It's easier to design circuit to have like 0, 1, and so on, so forth. Yeah, actually, in the past, people use this kind of lateral lock. Like sometimes still use lateral lock. If you can of course compute entropy using lateral lock here. If you use lateral lock here, they have a unit called lat here. But most people don't use lat anymore because of the reason I just mentioned. Because people is nowadays will think more like computers. But in the past, people sometimes I'm also like the only difference is just the unit, because if you do a log base 2 instead of lateral log, I have, let's see, for example, log base 2 of px. Let's say this is in terms of bits, right? This will be in terms of bits. this is equal to what? It's equal to lateral log of px over lateral log of 2a. You agree with that? So this is I just know that like if I have log something like for example a constant base n is equal to just equal to lateral log of c over lateral log of n, right? Something like that. So this is I essentially just doing the same thing here. Now, but then like this is equal. This is these two are equal, right? And this is equal to minus log 2 exponential minus log px here, right? So these things will be in terms of let now. This will be in terms of bits here. So you see the difference is like, for example, if I have like in the unit 10 bits, it's equivalent as like how many let will be equal to okay, I get quite let's see. Time bits. Yeah, I think so. Yeah, it should be something a log base to 10 times 10 let, something like that. Yeah. So anyway, like okay, it doesn't matter. Maybe okay, I could make mistake of it. It either 1 over log 2 or like log 2. It doesn't matter. I think it's a yeah. I think it's a I think it's a lateral log. Yeah, this should be it should be okay. So because this should be like smaller than 1, right? Yeah, it should be smaller than 1. Lateral log. Let in terms of let should be a bigger unit because the base base e is like bigger than 2. Yeah. Okay. Yeah. So, but anyway, like the difference is just a unit, so therefore it's not very important. So, okay. Anyway, I we digress quite a bit from like what I was originally like to talk about, but it's okay. I think this is good because then I can make sure you guys are for account like we are all at the same page. Oh, wait a sec. We have some question left behind. Maybe we can go back to some of them. We went through that. Now, okay, now we can really go back to this question here. So I assume that you get a little bit more understanding of HX now. And again, the HX is just the amount of information of random variable X, and more precisely, how many bits are required to, on average, to store X losslessly. So now if we argue like the conditional entropy, the conditional entropy is say, given Y, some helper information Y, on average, how many bits are needed to store X losslessly? So as I said, like we can do a forward approach to show that like the number of bits required will be exactly hx given Y. That's apparently that's why we call it hx given Y. That's very nice kind of like definition for that one. And so we can just like think of like forward argument. Basically, we can construct a scheme showing that like as long as the number of bits is less than the weight the number of bits okay like available to store the samples on average is larger than hx given Y, then we can compress and recover X losslessly. Now the scheme as I mentioned will be like, for example, we have like 10 different outcome of Y here. So let's say Y can be 1 up to 10, let's say. And we will just have like 10 encoder-decoder pairs for each of the kind of conditional probability. P is given 1, P is given Y equal to 1, P is given Y equal to 2, and so on and so forth. And now, so what we are going to do is say, we just switch encoder-decoder pair, like each time we receive a different Y. So for example, I have a situation here. Y for the first time step is equal to 1, second time step is 1 again, third time step is 2, then 1, and so on. Now, the question that we have earlier is that like, if we only consider um, the case when y is equal to 1, then for those cases like that's for basically like when that's when I at the time instant 1 2 4 again, and for that cases like how many bits are needed on average to store x given y. Of course, you can say how many bits are needed will be like you can add as many as you want, but like what I mean is like at the minimum, how many bits are needed per sample to store x given y. You should think along the line of the distribution again. So when I have y equal to 1, x will be, for this case here, like let me just say like for this time instance here, I have like the distribution is like px given y equal to 1 essentially. And then like uh, for example, like for case situation, I mean for times instance step 3 here when y equal to, it's like I have a distribution px given 2, right? Or like this. X, yeah, doesn't need to be like uniformly distributed. For example, like I can have like uh, when x equal to 1, I can have a distribution like that. Like let's say, or okay, if it is discrete, maybe like I draw something like discrete, like anyway, something like that. Maybe when x equal to 2, I have a totally different distribution. Let's say, sorry, not x equal to, sorry. I mean, when y equal to 1, I can have a distribution like this red one, and y equal to 2, I can have another distribution, something like this, like the green one here. Mm, you can't tell now. Actually, what I'm asking, what I'm giving you is does not have sufficient information to give a numerical value. But here I'm really looking at the expression, like yes, something like that, right? Oh, by the way, be careful. X should be like capital X here for the same reason I mentioned. Um, because we are looking at the information of random variable. So what is hx given 1 mean here? So it's something like hx given 1, right? That one will say something like expectation minus log probability. Okay, I should write a big x here. Big x given 1. Given 1 mean that y equal to 1, something like that. Or like something like you can write out the expectation and say px given 1 log p x given 1 for minus sign here. X is the alphabet here. And similarly, I can argue like, okay, for the second case, I will have like, when I have like y equal to 2, I will have like hx equal to 2 is the number of bits needed, right? So therefore, maybe I use space here. So there on average, right, how many bits are needed? So I will, for example, if I have a small y there, hx given small y, right, will be when for the time when y is equal to small y, on average, the number of bits required will be like small y, right? Now, how much information on average now are needed to store x? So therefore will be weighted sum by the probability of y, right? So it should be something like that, right? So therefore, actually should be the definition of hx given y, is simply the for the so okay, does it make sense? I guess first, I hopefully it makes sense. So for each time instance, or not each time instance, each time we have a small y there. For those cases, the number of bits required is h is given small y here. Now, how many times that we will get small y will be proportional to the probability of y, right? So therefore, we weighted sum that. Okay, so that's great. So and then okay, what's this? Let me just substitute back this back. It's this is let me write it. So this is y. This guy is sum over x px given y. I have a minus sign here. Log px given y, right? Right. This is hx given y times py, right? Now py multiplied by px given y, I will get pxy, right? So I can write this xy together. I have a minus sign here. This is pxy log px given y, something like that. So this is basically hx given y. So and oh okay, I think I still didn't get back to the Converse proof, but maybe okay. Let me defer a little bit later because it seems to me like I spend more time um, than I expected again. So I want to make sure because I have assigned the homework assignment like mentioning conditional mutual information or like mutual information and so on and so forth, that kind of stuff. So at least I like to mention those before I get back to, let's say, the Converse proof and other things. So now I guess okay, h is given y now I hope that hx and hx given y is clear what they are now, the physical meaning and the expression as well. So maybe I write down the hx again and maybe I just erase most of the stuff here. So hx now is it's expectation minus log p big X here, or I can write as a sum over px log px x here, something like that. And matrix y is like this. Hx given y. And again, the hx is just how much information of x per sample. And x given y is just hx given y is just how much information of x remaining x when y is given. Now we can let me just quickly introduce something known as the mutual information because I mentioned that in the homework. So the mutual information is just think of like what's the remaining information, or like I should say remaining, what's the shared information between x and y. So something looks very natural, right? If you think of like h is given y, h is given y is like how much remaining information of x given we already know y, then we expect the difference there like will be something like meaningful, right? So hx, so you can almost, let me just state it as like some kind of like definition here. So mutual information of x and y will let me define as a hx minus hx given y. So Or you can imagine like hx given y plus ix y here should give me hx. So something like if I think of like how much information is shared between x and y, and I add that with the remaining information of x, given that we know y, should get back the total information of x. Now, if I go here, we look at this. This is basically, I just substitute all this thing here. I have xp, x log px, right? Something like that. I have a minus here. Let me write plus instead, like xy, pxy log px given y, right? And know that like here, it doesn't depend on y, but I can add y here. Let's add y here. Or like, let me write like this first. Like px here, I can write it as a marginal of the joint distribution pxy, right? So let me, px is actually pxy marginalizing the variable y here. So then I will have something like sum over xy now, and pxy log px minus log px given y, right? Something like that. And this thing here will be log px given y, right? And I can use base rule. Basically, px can be written as this can be written as a log px. Wait a sec. Oh yeah, I can write using base rule like this one written as a pxy over py, right? So therefore, like this guy here is like log px py over pxy. Yeah. So let me just write down the whole thing now. So it's like pxy. I can just say inverse this thing here and absorb the minus sign into that. So I just flip the numerator denominator of like log pxy px py, something like that. And by the way, like for distribution like this, I have like something like if I have a qx log qx px, something like that. Or okay, like maybe I don't use x here to make it confusing. Let me use c here, let's say. So basically, I have like two different distributions, p and q, on some random variable c here. So here, like you can think of x and y as some joint random variable, right? So I have one of them have a distribution pxy, and another have distribution like distribution pxpy. And this thing here, there's a name for that, like it's known as KL divergence. There's also some people call relative entropy. Now back Lieber divergence. I don't know how to spell it. Yeah, something like that. But yeah, just call it KL divergence. It's easier. And so therefore, like this guy is really a KL divergence between P, X, Y. Don't worry about like I will go pretty in depth of KL divergence, but I'm just kind of like jumping ahead a little bit. But at least I like to make sure I introduce a mutual information because it's mentioned in the homework problem there. So and more precise, I ask you to compute some mutual information. So okay, let's pause here and come back maybe 3:30. Sorry, like 4:30, and then like yeah, we'll continue maybe talking about the Converse. Okay, let's resume. And let's see, where's my pen? Okay, he's here. Um, and so we mentioned, okay, this one is the mutual information. It's just the difference between like hx and hx given y. I know that like the mutual information is symmetric. If you look at the expression here, eventually it's equal to this one here, right? So we have like the mutual information is a, as I mentioned, is the Carroll divergence. Okay, let's forget about Carroll divergence because I didn't formally define that yet. So it's like this like kind of like I have this log pxy and py here, right? So what I want to say is like apparently I have ixy is the same as like iyx here, right? Symmetric. So therefore, like this one is also equal to hy minus hy given x, something like. And let me again, like I don't know whether I should erase or okay, maybe I just use another a blank page here. So let's say ixy, as I mentioned, is I should be just if you derive that, like okay, or like so hx minus h is given y is also hy minus hy given x, and it's like if we expand out, it's like pxy sum over xy log pxy pxpy. This is ixy. And in the homework problem, I also asked you to compute like the conditional mutual information like ixy given w, let's say. So what does this mean is that this is essentially equal to the ixy given some w, small w, and weighted sum over w here. Oops. Weighted sum by pw. Okay. So what does this mean here? It's just we will be okay. We'll be considering not John probability or like pxy, but like John probability xy given w. So in the sense that this one is actually equal to, maybe I just write here, equal to sum over x y pxy given w log pxy given w over px given w py given w, something like that. And let's see. And of course, this will be like something like x, y, w. If I merge these two summation together, it's sum over like x, y, and w. And I have like pxy given w multiplied by pw will be pxyw, and log pxy given w px given w py given w. So, but anyway, like I guess this part is a most important. Like, but the thing given w can think of just it's similar to our definition of hx given y here. You can interpret hx given y as weighted sum of like p, weighted sum of like hx given small y and weighted by py here. So for each of these small y, you have a different distribution of x, right? So here, like for each distribution, each different small w, we have a different joint distribution of pxy given w and px given w and py given w. And so we can define this ixy given w. And then like we will just weighted sum them, we will get the ixy given w. But here we can simplify a bit more. So this one, let's see, I can write it as, let's see if I can. I will argue basically this one is actually just equal to hx given w minus hx given y w, w and y. So let's see if I can see that. So here, I can use base rule. Let's see. Hx, this thing here, hxy, sorry, pxy given w over py given w is just equal to px given yw, right? So, or you can think of like py given w times px given yw. So you look at y and then you look at y given w and look at like given y and w and multiply px here. This will be like px y given w, right? So this is plotted here. So then therefore like this one here is equal to x y w p x y w log p x given y w for log, sorry, not over log over p x given w. Then I can write it as a minus x y w p x y w log p x w plus actually better write minus x y w p x y w log p x given y w, right? So okay, I want to mention that, but what is this thing here? What's this? What's this? I mentioned that a moment ago, but can you see that? So it's a question of what's this, like h of what? Oops, yes, it's just hx given yw, right? Yeah, this is hx given yw, and so what is this? Oh, I should say that this whole thing here was this thing here. Yeah. Oh, you mean the second one is a okay. The first question or the second question, like this second term here. So this term is a h is given yw. The second question, yeah, this one, yeah, what was this? Like so this one, Yes, this one is hx given w. Yes. Yeah, because you look at like, okay, this one here, sum over y xw, but like y is like kind of a dummy variable here. I can sum over y marginal because this does not depend on x and y, right? So it's like this is a constant with respect to y. So I have like xw log p x given w here, right? Minus and sum over y p x y w. So this will give me p x w, right? So p x w, I mean minus log p x given w weighted by p x w. This will just give me like h x given w. Yeah. So okay, in conclusion, is I if I have this thing, if I define my conditional mutual information as just a mutual information with this conditional variable, think of like for different helper variable for different instance of this or different realization of W here, we weigh the sum of this like conditional mutual information ixy given W weighted by the probability Px here. Oops. Okay. Weighted by this Px. Oops. Weighted by this Pw here as our conditional mutual information. Then we have expression like this, and this will end up with just h x given w minus h x given y w. So of course it's symmetric, so therefore it's also equal to hy given w minus hy given xw. So to compute stuff like this, there are many ways for you to compute it. Like you can compute directly using like probabilities like this, or like you can compute individual of these conditional entropies, and then compute the final mutual information, conditional mutual information. So okay, I mentioned this like a little bit ahead of like what I plan to mention them earlier, because we have this in the homework assignment, but I think like knowing this is sufficient for you to complete the homework. So okay, now let's go back to what I mentioned at the beginning, that I like to talk about the Converse proof again. So just like we ended last time. So the Converse proof of source coding theorem. So basically the statement is like, if we compress more than the entropy, so if the weight is less than the entropy hx, then there'll be lossy, right? So the compression will be lossy. So, but we will prove a counter argument, so it's easier to prove. We will prove like instead of essentially the same statement, but this statement is essentially this also means that like if things is lossless, so because this is like A then B, right? A then B, it implies that it's equivalent to log B then log A, right? So if it's lossless, then the weight has to be bigger than hx. So this I guess the first statement is more intuitive to say, but the actual proof will basically prove the second statement. It's like if it's lossless, then the weight will be larger than hx. So first of all, like what's the weight? So we have the setup is like this, right? We have the encoder here. So we have x is like, let's say a sequence coming in, and maybe xn here, and then it kind of compressed into a code word. So we take a sequence of x that get compressed into a code word, then we cover that like into x hat n. Now, if it's lossless, it means that like the probability that xn is not equal to xn hat should goes to 0, right? So this one should go to 0. And we say that like there's a Fanose inequality. We didn't prove that last time, so we're going to prove it. But we try to use that, but I guess I ended quite pretty wash. So maybe many of you didn't actually get it. So so we will use the Fanose. The Fanose, the idea is very simple. So if the probability of error, this is essentially the probability of error, right? Probability of error is goes to 0, then I will have something like the hx n given c. So this is a per sample, say a little per sample. So it goes to 0. So it makes lots of sense because if you think of that, this is a given the code word, the remaining information of the original sequence should per sample wise it goes to 0. Of course, right? If there's no error, this decoder is like kind of deterministic. So therefore, like given C, I know X hat end out immediately, right? I know this like precisely. And if there's no error, then knowing this is the same as knowing this. So therefore, like there should be no information, remaining information of Xn if I know C, right? So this seems to make sense. So I will prove later, just immediately later. But let's again like try to show the Converse proof first. The Converse statement is basically saying that like if it's lossless, so essentially these errors go to 0, then the weight has to be bigger than hx. So what's the weight? The weight is like hc, right? So I have hc here. And I want to look at per sample, right? So I would just say, because I take xn as a sequence, basically n samples, I'm going to compress it, right? So therefore, like the per sample weight will be this one, right? It'll be like just hc over n, right? So hc over n, I can write it as a is actually I let me make it a more rigorous. I add an epsilon here, and this epsilon here can make arbitrarily small, can be arbitrarily small. So I want to argue that like these can be bigger than hx, right? So if that is the case, so of course I need a condition here, say lossless, error free. So then this basically proves the Converse pathway. So even though I add the epsilon, it seems to be cheating, but know that this epsilon is arbitrarily small. I can make it arbitrarily small, and and this overall is saying that like my weight has to be bigger than hx, right? So if I make the if I allow to make epsilon arbitrarily small, then this, if I am able to show this, then basically it also show the statement, right? The original statement. So you you so okay, actually I put this epsilon here, just try to make things rigorous. So because I immediately I can write something like that. It's that like this will be bigger than 1 over n hc plus h xn given c here. So this is like just Fano. So we say like by Fano that like h xn given c will converge to 0, right? This will converge to 0, meaning that like, okay, what do we mean by converging to 0? Meaning that like for any epsilon bigger than 0, h xn given c over n is less than epsilon for some n, right? So therefore I can put any epsilon here. I can put any epsilon here, and since by final this will converge to 0, I know that I can pick some n. N has to be big enough, but it doesn't matter. It will be some n that exists such that epsilon will be bigger than like 1 over n hxn given c. So therefore I will have a statement like this. So and then and then this will be just equal to h C given, I'm sorry, HCMXN, right? And then this will be the 1 over n. I can move the other way one is HXN plus HC given XN. Now, I asked you last time, maybe I don't know whether I should ask you this time again. What was this? So yes, 0, right? So this is 0 because I knowing xn, like C is just an encoded value of xn. So and encoder and decoder is supposed to be deterministic. So knowing xn, I know C precisely, right? So therefore knowing xn, there's no remaining information of C. So therefore this is just equal to 0. So therefore this is equal to 1 over n xn here. So because x is IID, so it's just equal to n hx1 plus hx2 and so on and so forth. And each of this is just equal to hx. Or maybe like let me write it more rigorously here. So here I can have some kind of chain rule here is equal to hx1 plus hx2 given x1 plus hx3 given x1, x2, and so on and so forth, right? Blah, blah, blah. Up to hxn given xn minus 1. So by the way, this is like some kind of like shorthand notation is convenient in information theory context. Like people like to write something like x given, for example, y n here. It usually means that like y this is just a shorthand notation of like y1, y2 up to yn, something like that. So here, therefore, is a shorthand notation for x1, x2 up to xn minus 1. Now, because each of these variables are actually independent, right? So therefore, hx2 given x1 is just equal hx1, hx2. hx3 given x1, x2 is just equal hx3. So think of that like, okay, we did, I'm not sure. Yeah, I think I didn't show that, but just think of that intuitively. If they are independent, then having the variables doesn't help at all, right? Think of the context of what does this conditional entropy means. It just means that like how much remaining information of x2 given that we know x1. Of course, it's x1 is totally independent of x2. The amount of information of x2 given x1 will be just equal to the amount of information of x2 itself, right? So therefore, like these conditions will just like it's not there. And because it's IID, I just have like, I mean, they have the same distribution. Therefore, I will have n hx, so many of them, right? Then over n, I will got cancel. I just have like hx. So therefore, I indeed I get something like wait. I put the inequality incorrectly. Is that? Oh yeah, it's correct. It's correct. Yeah. Therefore, I will have like 1 over n hc has to be bigger than hx. Basically, the weight itself has to be bigger than hx. Okay. So I hope this is clear. So now let's try to show the Fanon's inequality. So for Fanon, again, the Fanon is basically saying that like if I have the setup that we have there, xn, I have the encoder, I'm compressing that into C, and then decode that into xn hat. HC, sorry, hxn given C should converge to 0, or what does that mean is like for any epsilon, hxn given C will over n should be less than epsilon as long as I, for some n, okay, for some n, or as n goes to infinity, something like. So I can find a big enough n such that this is like less than epsilon. Okay, so what I'm going to do is I will introduce some helper variable here. I will call something e, some kind of helper variable. That is just an indicator to indicate whether there's an error or not. So if I have like, I say e is equal to 1, if like xn is not equal to xn hat, right? So in this case, this means that there's an error. So otherwise, it will be no error. So we say equal to 0. So I have a helper variables like this. Now then I can write hxn given c as or maybe like think of like this plus he given cxn okay, maybe I make it a question here. This is equal to what? H blah blah given blah, something like that. Like this is equal to what? Oh, wait, you have xn given c here already. So you have xn given c added with like this additional things, right? Oh, uh, I don't mean to jump ahead. Maybe that is equal hxn given c, but what was this? Something like that, but need to be careful, like which one is which. Okay, think of like always, what does that mean? This is like knowing C, what's remaining information of xn. Now, knowing both added with the information of like knowing both C and xn, what's the remaining information of E. So these two added together will be like what? Yes, yes. What's the information of xn and E, knowing that C, right? So this is a xn, E and C, something like that, right? So then I can rewrite like hx and given C as a what? H x and E given C minus H E given C x n here. So okay, now another question, what is this? No. Okay, you want to pay attention what E is defined. E is defined as just an indicator function. Indicator values can only be 1 or 0. And it's 1 when there's an error. That's basically xn is not equal to xn hat. And it's 0 otherwise. So for one thing, you know that like E is just binary. It cannot be more than 1 bit because yeah, only have 2 values. But you can say more about E. Sorry. I mean, for one thing, it's like this HE given by this guy says should no more than 1 bit. But I can say more about this HE given CXN here. Again, think of like what do you know when you know CMXN here? So you have the setup. You need to look at the setup as well. Now, remember also like encoder and decoder is deterministic. You have xn, you know C precisely, you know C, you know xn hat precisely. And by the way, you know xn hat, you know E precisely. So you guys are thinking or like, Oh, okay. So the setup like maybe look at this setup again. Like you need to do this is like this is related to this precise setup. Like um we cannot find the value without look at this setup here. So we have basically an encode xn. Like we have an encoder, right? Kind of encode this xn into a C. It's a code word C, and then we have a decoder like decode C back to xn hat here. So we have an indicator function E here. So basically saying that when x hat is not equal to xn hat, then is we have value 1, otherwise we have value 0. So the question is say, given C and xn, now you should think of like, given C and xn, what do we know? Given C, we know xn hat, right? And given xn and xn hat, what do we know? Yes, so therefore like what is this? Yeah, actually, it's just 0. No, remember again. Okay, very important is like what's the physical meaning of this thing? Like whatever hx given y or like hx given yw or anything. Like know that like what they physically mean is just that like precisely if I know y or if I know y and w here, how many bits are needed to store X such that I can recover X losslessly. That's precisely what does that mean. In a nutshell, or you can think it more intuitively, you say how much remaining information of X knowing y and w, for example. Now, in this case, given c and xn, I know precisely what is e. Then, of course, there's no remaining information need to be stored to recover e, right? So therefore, this will be simply equal to 0. Mm. Is that um, is that okay? So whenever you are given this thing, this is just a deterministic function of these given variables, then this conditional entropy just has to be 0, right? Because given this um, conditional variables, basically the variable that we are interested, the variable of interest is known, right? It becomes deterministic, right? So therefore, there's no remaining information. Therefore, in this case, HE given CXN is just equal to 0. It's clear. I guess this part, I guess this is very important because um, 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 otherwise, if otherwise it doesn't make much more sense to continue like this. I want to make sure um, as those of you are here are following. Otherwise, it probably not very meaningful to continue continue forward. So so please ask any kind of question. It doesn't matter. Ask any questions. If you have anything doubt of. I'm sort of following. What I'm sort of following. Oh, okay, okay. You are following. Okay, yeah, okay. Okay, yeah. So let me repeat again. When this h is given y, whenever maybe I just say h is given y. This is what it's saying. It's just how much information of x are there as long as you already know y. So therefore, for example, whenever we have something like fx given x is always equal to 0, because if we know x, this is just a function of x, right? So here, of course, I assume whenever I write a function, the function should be deterministic. So knowing x this is precise. So therefore, it's just equal to 0. So for example, I can have h y plus 2 given y, this will be equal to 0. Or consider this y plus 2 is some random variable as well, right? So if this is a random variable, let's say z is equal to y plus 2. So now if y is random, z is random as well, right? But if we know y precisely, then we know c precisely, right? So therefore, in this case, this will be equal to 0. Because knowing y, there's no remaining information needed to store the value of c. Right? Knowing y, we know everything about z. So the same here as well. We knowing c and xn here, we know precisely what is e here now, and we don't need to store. I mean, any additional bits just to store the value of e, given c and xn. So since this is 0, so we have something like that. And of course, I can expand this another way, right? So this is equal to h x and okay, that's great. So this is equal to h this way, h e given c. Let me write better. Minus h. Why so bad? H e given c x n. Oh, sorry, this shouldn't be h e. H e given c and h x and given EMC here. So I just expand this another way, right? Now for HG given C, I don't care too much, but I know this is binary, right? So therefore, it has to take Okay, first of all, like I didn't show it yet, but you know, x given y, um, we mentioned that earlier that hx minus hx given y is the mutual information shared between x and y. And that's the shared information between x and y has to be bigger than equal to 0. We were able to show that. Like we will again, I will delay that later on. Like we will show that this is bigger than equal to 0, meaning that like hx is always bigger than hx given y. So this is reasonable also, like right, intuitively it's reasonable. Knowing some additional information, the amount of information or like amount of storage needed to store x should reduce, right? We always will need less number of bits to store x now, knowing some additional variables. So therefore, like uh, this is like these things sometimes people call it conditioning reduces entropy. So therefore I can claim that this one here is less than HE, right? And E is binary, therefore like it has to be less than 1. I know, right? It's binary, definitely I can store in 1 bit. So this thing is less than 1. And for this part here, yes, oh, sorry, this is a precise, should be a precise, I'm sorry about that. And this part here, I can split that into two parts. So here, therefore I can write it as this is less than equal 1 plus, and this I can write it in two parts. It's this is by definition of conditional entropy, this is essentially weighted sum of like hxn given e equal to 0 c and hxn given e equal to 1 c weighted by probability e equal to 0 and probability e equal to 1, right? So this is like just what we described earlier, like how we define a conditional entropy. We can always consider as a conditional entropy given some variable, um, given some particular realization, and weighted some by that probability of that realization. So now let's see. We have two cases here. Let's look at this term again. How about this term? Can you do you know what's the value of this term here? This one, hxn given e equal to 0 mc. Okay, yeah. Yes, actually it's the same argument earlier, but like probably a longer argument, right? So when e equal to 0, it means what? It means there's no error, right? So, and we know C, what do we know? We know C, we know xn hat. And when there's no error, xn is just equal to xn hat, right? So therefore, like, given xn hat, xn is nothing, right? So therefore, like, or like, yeah, it doesn't have any additional information, right? So this will be just equal to 0 here. So this term is gone. So we only have this term here. And if we look at this one here, um, again, I can, let me just write 1 plus, I can bound this one by hxn, right? Because I just say conditional length reduces entropy. So it's bounded by probability E equal to 1 hxn here. Okay. And hxn, we argued earlier, this hxn is actually just equal to n hxn, nhx, right? So therefore, like the whole thing here will be equal to 1 plus probability of error nhx, something like. So therefore, if we have dy n on both sides, so I have 1 over n h xn given c is less than equal to 1 over n plus probability of error hx. Right. Now, if I have probability of error goes to 0, then this term is gone. Then we only have this term left. So it means that like for any epsilon, as long as we have n big enough, we can have like this can go arbitrarily small, less than epsilon. So I mean, like, this can be for any given epsilon, I can have this like less than epsilon, as long as like n is bigger than epsilon or something like that. Sorry, n bigger than 1 over epsilon. Yeah. So yeah, but anyway, yeah. Yeah, this basically finished the proof for the final. This is it. So then then also conclude the proof for the Converse proof of the source coding theorem. So okay. So next let's see, next what should I do? Let me just take a look. Okay, yes, I guess I okay, maybe I will start with like showing like some of the properties that we mentioned, but we never prove that. Like for example, like we say hx, like for example, like if x take like values 1 to up to 8, so we know that this is less than 3 bits, right? Or essentially like with a bound, something like that, like hx is less than or equal to the alphabet size, oh sorry, less than log base to the alphabet size, so many bits, right? So we kind of argue that, but we never kind of show that. So the simplest way is to show that using something known as the Yangtze inequality, I don't know, so-called Jensen or Yangtze. So it goes something like that. If you have a function, it's converse, f is converse, fx converse function. Okay, let's see, like, do you guys have any kind of maybe A, B, and C. Or I was just drawing a 1D function here, fx. I say this is x here. So which one is converse? Yes. Um. Yeah. Actually, I guess the name is like kind of like annoying. Actually, this is Converse. Yeah. Yes. Yes. B is concave. Like it looks like this is to me like it will. I would like to call this like Converse also. No, I think like this the convention problem also. I would like to call this like convex also because like, this is like a convex lens. Like, but yeah. So but yeah, the convention they call it this is convex. So this is concave. This is neither convex or concave. So but you have idea what do you mean by convex? So this can extend to high dimension, right? So if it's convex, you have some um let's say concave is literally a cave. Okay, actually I like that. This is not bad. This is pretty good. Yeah, yeah, yeah. But yeah, but so first sorry, I guess I also get quite a bit because I know why you pick that to call it Converse because I mean like we study I mean like what do we say optics like in high school or something, right? This is like a convex lens, right? So this is a convex. Yeah, of course, there's two surfaces. And it just seems to me that this may be a okay. I don't say more, otherwise I will get people confused. But I guess this is good. Like concave is like a cave. Yeah, that's nice. This is like a cave, so it's like concave. Yeah. Okay. So the other one is convex. So, but anyway, so for convex function, we can extend to yeah, I guess I can draw some bat. Yeah, but I'm very, yeah, I don't know. I can draw bird, but I know how to draw bat. So, yeah. So, okay. So if we try to extend convex to high dimension, so maybe, yeah, okay, I don't know how to draw it anyway. So just imagine in high dimensions. Yeah. Yeah, but I don't know. Maybe we can shuffle later on. So yeah, but the cave is a good yeah good way to memorize that. I guess yeah. Um. Yes. Okay. So basically, if I converse, like let's say converse, if I draw a line here, so if I have any points here, let's say I have x1 and x2 here. So I have if take any points like linear combination between this line here. So I have like let's say this point here. Let's say this is like p. Okay. Let's just have one half of them. Maybe just take some value. Like so at the middle, like x1 plus x2 over half of them. So of course, this point on this line will be like x1 plus x2 over 2, and also like the the height here will be like f x1 plus f x2 over 2, right? And the value here on the curve, on the other hand, will be f x1 plus x2 over 2. So in general, like for a convex function, we have property something like f, let's say even for high dimension, let's say if I have like x1 and x2, this is vector, right? If I look at the weighted sum of these 2 points here, let's say weighted sum like p x1 plus 1 minus p x2 here. So these points should be below the linear combination, basically f x1 p plus 1 minus p f x2, something like that. So for all x1, x2, something like. So if this you can show this, then you have the function is convex. And Yangtze inequality is saying something like, if you have a convex function, then the expectation of that convex function will be so think of like what is the expectation of the convex function that is similar to this one, right? To this on this other side, right? So you take weighted sum for f values, so you have a bunch of f values, or I can write this, for example, this would be like f small x px sum over x, right? So this is similar to the sorry, I don't know which one I should say, right hand side or left hand side now. If maybe I write it here, f px1 plus 1 minus px2. Now I can call this a left hand side now. Yeah. So this is similar to the right hand side, right? Maybe I try to use more colors. So on the other hand, if I consider f expectation x, this is more similar to the left hand side, right? So it's like I first take an expectation. This is like the expectation of something, and I take the function of that. And just look at the definition. Actually, you will expect something like this, right? This will be bigger than equal to expectation fx will be bigger than f expectation of x. So I think like for discrete, I mean x with discrete number of or finite number of outcomes, you can show it quite easily. Actually, yeah, I'm not sure it's easily, but by induction, so you should be able to show that. But we won't try to do it. Like for continuous case, it's a bit more evolved. But intuitively, I guess hopefully it's not very hard to see. If you have the function is convex, just by the definition alone, you will expect to have say something like this. And this is known as the Yangtze inequality. And if this is f is convex, so of course if f is if maybe you use word here, if s is concave, then we will have the exact opposite. So you have like efx is less than equal to fex, something like that. Okay, so now, okay, let me erase some of this here. So using the Jensen or Jensen inequality, we can easily show that the upper bound of hx is bounded by log the number of outcomes. And so basically, because we know that like hx here is just equal to expectation minus log px, right? Now we think of like what was the log here, or let me write it like this: expectation log 1 over px here, and log function. Okay, I can think of this as a random variable here, and log function is like this, right? So log function is concave. So therefore, like if it's concave, so I have an equality like this, right? Concave. So therefore, I have expectation of fx is less than like log expectation 1 over px, right? And expectation of px is what? It's just log sum over x px 1 over px, right? And this will be just, and this is a sum over all the outcomes, right? So this will be just equal to log sum over x 1 here. So this is just counting the size of the number of outcomes here, right? So therefore it's log x here. So that's, we get that the upper bound here. That's this one here. So And yeah, I'm thinking, okay. Mm, yeah, it's okay. It's okay. I'm thinking like whether I should introduce differential entropy, like say more about differential entropy now, or like say more after we um yeah, okay. I will stick to my original plan. I'm going to like talk more about differential entropy, talk a little bit of differential entropy first, then to look at like again like go back to talk about Carrier divergence and so on. So um for the for okay, for our discussion we kind of like focus on variables that are discrete. So if we have continuous random variables, so know that like we still have the same thing here, like if x is continuous, like continuous, so I can still like define the entropy as a minus log px here. But know that like this one is not the probability anymore. Like it's not the probability mass function, it's the probability density function. Or if you look at some textbook, like to use F instead, but here we'll just use P. But know that this is actually the PDF. This is PDF here, probability density function. And actually this will be typically use a smaller kind of lowercase h instead, like to denote the entropy here. People call this like differential entropy. Note that like this expansion expectation of expand out, this should be an integral, right? Because now this is PDF, so we say something like px log px here, dx, right? Um, and so maybe I just do some numerical example first, I then go further. Um, so, but maybe like before that, like I want to kind of like mention that like the same kind of like analogy can be used here for continuous variable as well. For example, I can define the conditional uh, entropy, differential conditional entropy, uh, just as the expected value of minus log p x given y. And so this would be like, again, it will become an integral p x y log p x given y. So it's like dx dy, something like that. And you can kind of like define mutual information as well. As a this essentially become like pxy log pxy px py dxy. So this is a also is a same kind of expression that h is given y. I'm sorry, h is minus h is given y. So everything is very similar, just like everything will be replaced by a kind of a sum. The sum will be replaced by the integral. So now let's look at a very simple numerical example. Let's say if I have a uniform distribution, let's say I have the values of x can take values from have the interval, like let's say from 0 to a, let's say, and then it's uniform, so it's a 0 to a, and so therefore the probability is just 1 over a. Oh, by the way, like let me just ask you now, like very quickly. So what is hx here. So you can just like use the definition here. So to find what is hx, what is hx? What's this small hx? Yeah, that's basically the definition of small hx here. So you can evaluate that way. So this is like basically this is like the px here is like this. So what will be hx? Actually, rather than like dealing with this integral, like you will get the solution quicker. Like just look at this here. Oh, it would depend on A basically, right? It would depend on A. Oh, okay. Yeah, A is a constant here. Oh, here this distribution is like uniform. This is uniform. So px is just a constant, right? So therefore it's just equal to 1 over A, right? For A is between 0 and 1. Sorry, 0 to n. Sorry, not A for x between 0 and A. Okay. And 0 otherwise. Oh, sorry, like, yeah, my handwriting. This is A here. So this is a PDF. So the area underneath has to be equal to 1. Yeah. Yeah, A times 1 over A should be equal to 1. Yeah, that's so that's, yeah, that's the case. Wait, sweet. It will depend on A though, right? So this should depends on A. Yes, yes. Something like that, right? So you have hx is a expectation minus log px, right? So and what's px now? Px is actually a constant for actually for what do we call that, like for the support of that x here. So therefore, like that constant is just equal to 1 over A. So I have log 1 over A here, right? Minus, so that would be like log A. Right? And it's like expectation, this is just a constant. I can pull it out. So it's like just expectation of the constant is just itself. So it's just equal to log A. Right? Just equal to log, simply equal to log A. Yeah, but actually one thing is interesting. You see that if I change the value of A, I can take any value of this conditional entropy. And I can even go negative in the negative regime, right? So I can take A, for example, to be one half, then I will get like log A is equal to -1, right? So I can have a negative value for the entropy, for the differential entropy. Actually, I can get like negative infinity if I want. If A is a super small, it's like basically the distribution is like a delta function. Um, but know that like for hx, you cannot get negative. Hx is always bigger than 0 because I think of like the physical meaning is like how many bits are needed. That how many bits is like something physical, right? It has to be positive, right? It cannot be something negative. And also, if you look at the expression, it's a sum of px log 1 over px, right? Something like that. And so px is also always less than 1. So for a PMF here, right? So therefore, like this thing is always bigger than 1, or sorry, always bigger than 0. So therefore, the whole thing is always bigger than 0. So for the original entropy that we discussed for the discrete random variable, hx is always positive. It cannot be negative. And the unit is bits or less or whatever. It has some physical meaning here. So therefore, like be careful when we talk about differential entropy. That's less linked to the physical meaning here because like something could go negative. That definitely, like in terms of information, it doesn't seem like it has to be. But we will connect that in with the regular entropy. You see like how comes this is still can be physical, or maybe we can do it immediately. Let's see like what should my plan be. Um, oh, by the way, I have 2 minutes or 7 minutes. I always forgot like it's 5:40 or okay, 5. Yeah, okay. So okay, let's do that. Like let me immediately try to connect entropy and conditional entropy, sorry, entropy and the differential entropy. So the way to connect that is like, let's say if I have like a continuous random variable, let's say I have x here, right? I have x here, this is continuous. Now I'm going to discretize as I quantize it with to some quantization sub delta, and the variable I call x delta after quantization. So now this, because this thing is discrete, right? I can talk about the discrete entropy here, right? Just x delta here. And here, this one is continuous. Continuous, I can only talk about hx, right? So I want to see like how hx delta and hx are related. So I will have hx is let's see, px minus log px dx, right? Um, and hx delta, let's say hx delta is what? Is px delta log px delta. This I have a sum instead, sum over all the values here, sum over all this x delta here. Now, how do I relate this x delta and x here, p here? So think of like original, like the I I have x here is continuous, right? So maybe um, maybe this is like px here. This is a x here. So px delta, let's say this is a after quantization, right? That's a delta step sign here. So this px delta should be approximately equal to px times delta, right? So, or like maybe, how do I, maybe I should differentiate that. Let's put a delta here also, like the distribution, like p delta, px delta like that. So p delta x delta is like the probability for for taking value x delta should be approximately px delta delta, right? Something like that. Maybe right? This. Like that, right? Okay, that's fine. And then this will be, I can expand that. I can have log px delta p delta x delta p delta x delta log delta. And again, like p delta x delta here, actually, I can rewrite that. It is approximately, this maybe I should put an approximation here. This is approximately px delta delta, right? So okay, this thing here now is a similar to, I can move the delta on this side. I put the delta here. Then this thing here is like an approximation of integral, right? This actually approximate px log px dx, right? When deltas go to 0, this is approximately equal to that, or like approximately equal to h small hx, right? And this side, I have like log delta. Delta is just a constant. I can pull it out. So minus log delta. And this is just sum over all the probabilities, just get 1. So therefore, I will have like just minus log delta. So what I have is like, okay, in conclusion, what I have is like hx delta will be approximately equal to hx minus log delta. So I don't have any physical meaning for the differential entropy yet, but if I try to quantize it, I can relate to the reality almost. It's something like the amount of information of that quantized value will be like the differential entropy. That when if like the original distribution, I have a higher differential entropy, there's more information, but it won't be physical until I link to the quantization step size. I need to minus log delta, where delta is the quantization step size there. So let me give a very simple example first, like maybe to end. So let's say we have the distribution we have earlier. Let's say I have like A is a continuous distribution. That A is a equal to 10. Let's say like maybe again just a random variable X is a uniform, like takes kind of like 10 values here. So I have hx, as I mentioned, will be like equal to log 10, right? Log to 10, something like that. Now, if I try to quantize the value, for example, I cannot store the continuous value, right? But I can store the quantized value. I can ask, like, if I quantize x into x delta, let's say delta is like 0.1, let's say, how much number of bits are needed to store the quantized value? And the number of bits will be simply equal to log 210 minus log 2 0.1, and that will be something, something, something. So that will be like in terms of bits. Yeah. Okay, I guess I will repeat example like this later on. So, but this is a one thing pretty important, and yeah, you should have sufficient things to complete the second homework, and so I will see you guys next week then. So, and if you have any questions, just feel free to drop me a message in Discord, or like just, yeah. It's actually better to send me a message to Discord. Yeah. Okay. See you guys. Bye now.